Hi. In my video about external calls, I showed an assembly code to compute the famous inverse square root function as in the Quake source code, but I think it's originally from Silicon Graphics. And it's obsolete because we have an assembly instruction that does the same, but much faster. Anyways, here it goes, the famous fast inverse square root function. The overall idea is to solve the equation y equals 1 divided by the square root of x. There's a tool to do that, and it's written plainly in the code. It's the Newton-Raphson method for nonlinear equation solving. Yes, there will be math in this video. Let's say we want to find where this curved line intersects with the x-axis. It's the equivalent of solving f from x equals 0. The first thing to do in the Newton-Raphson method is to pick a point close to the solution. It's our first solution point. We are going to move this point closer to the actual solution step by step. For that, from this point we search the line that is tangent to the curve. Where this line intersects the x-axis will be the new solution point. Then we repeat this tangent line intersection with the x-axis. We are moving the point closer to the solution. Unfortunately, if we pick a starting point too far from the actual solution, the method can go wrong. Here the tangent points us in the wrong direction. Then by this game of picking tangent lines and new points, we circle around a point that is not our solution. So picking a good first guess is important. In math it is written like so: xn and xn plus 1 are our solution moving towards the actual solution, and f prime means the derivative. In our case, we want to solve y equals 1 divided by the square root of x. That's complicated, so we start by squaring the equation. Y square equals 1 over x. We can now easily move x and y square around and get x equals 1 over y square. Then we bring back x and obtain 0 equals 1 over y square minus x. This is a function of y that equals 0. We can use the Newton-Raphson method to solve that. The derivative is minus 2 times y to the minus 3. We plug that in the iterative solver for y and obtain this horrible thing. Let's start by removing this y to the minus 3 from under the fraction. If we simplify the fraction and perform the multiplication, the fraction gradually becomes nicer. Let's isolate yn to finally obtain yn plus 1 equals yn times 3 halves minus x over 2 times yn square. That is precisely what is written in the code. The only thing to remember is x2 is 0.5 times x. This is a bit confusing because in the original function code this part is at the top, but fundamentally these two parts of the code are about using the Newton-Raphson method to get a good solution for y equals 1 over square root of x. So the next problem is to find a good approximation to start the Newton-Raphson method. Let's talk about how numbers are stored in the computer's memory. These two lines are the same but reversed. We can think of the memory as a sequence of boxes that contain something. Each box has a number. In the C language, the symbol end indicates the address, and the next letter indicates the content at that address. The parentheses indicate a casting operation that changed the type of the variable. So here we cast the address of y into the address of a long integer. That originally was the address of a float, and using the star we store the value at this address in I. Using that weird operation, we have the bits of the float as an int, without changing their value as we would have by simply casting y into I. And as mentioned, the second line is the reverse. We take the bits of I and reinterpret them as a float using pointer casting gymnastics. We do this because in C we can manipulate the bits of an int. So now we need to know how the bits of a number are treated in C. A 32-bit long int number is literally a sequence of 32 ones and zeros. Here is an example. It's a bit cumbersome, so we sometimes write the same number using hexadecimal notation. In order to obtain the decimal value, it's simply a matter of adding the correct powers of 2. Here the bits at positions 26, 22, 21 and 19 are set. We obtain 73,924,608. Float numbers as defined in the IEEE 754 standard are quite a bit more complicated. Each number is composed of the sign bit, the exponent and the mantissa. The sign bit is easy, 1 bit. If it's 0 the number is positive, and if it's 1 the number is negative. In our case, it will always be 0 because square root of x is defined for positive numbers. The exponent is an 8-bit unsigned integer. I'll show later how we'll compute 2 to the power of e. For now, let's keep in mind that it's an integer, and we subtract always 127 to have the possibility to have negative exponents. So here we have minus 119. The mantissa encodes the sum of negative powers of 2, so 1 plus 1/2 plus 1/4 plus 1/16 equals 1.8175. This looks complicated, but there is method in this madness. Consider, for example, a number in base 10. Some people may consider it easier to rewrite it in scientific notation, and this scientific notation can be broken in this manner. That puts in evidence the different parts of the float. Here is the sign bit, then we have the mantissa part, that is 2 plus 0.72, and finally we have the base 10 and exponent minus 3. At that point we can retake our 32-bit float number and write it in base 2 scientific notation. Minus 1 to the power of s gives the sign. In base 2 scientific notation, the number before the comma is always 1. We had 2 in the base 10 example, but in base 2 it's always 1, and thus we don't need to store it. And finally the exponent, minus 119 we calculated. Thus our float number would be 2.72 times 10 to the minus 36. Now that we have a grasp on the number representation, we can do symbolic math. This is any float number and we will ignore the sign bit because we have only positive numbers. Let's take its log in base 2. I'll drop the base, it's always log in base 2. We can simply rewrite the expressions. The multiplication breaks into a sum of logs. And for small m, the log of 1 plus m is simply m. Log of m equals m plus e minus 127 is an important expression that we will need later. If we compare float and int number representation, we can notice that the mantissa is a sum of powers of 2. Well, so is the int representation. The int representation is actually the exponent e times 2 to the 23 plus the sum of the lower powers of 2. And if we keep in mind that 1 over 2 is actually 2 to the 22nd power divided by 2 to the 23rd power, then multiplying them by 2 to the 23rd gives us its contribution into the int representation of the number. So we have n int equals 2 to the 23rd times e plus m. But if we remember this important log relation from earlier, we obtain that the int representation of a number is related to the log of its float representation. Let's isolate the log as a representation of the int. This is the next important relation to remember. Now, if we come back to the inverse square root and take its log, we can express the log of the inverse square root as its int representation. But logs have interesting properties. The log of the inverse square root of x is minus 1/2 times the log of x, which we can also write as its int representation, and thus we can create an equation that links the int representation of y to the int representation of x. Let's solve that. First perform the multiplication and move the 127 to the right. The half 127 and the full 127 combine into 3 halves of 127. Then we multiply everything by 2 to the 23rd power. We obtain that y int is minus x int over 2 plus some complicated constant number. Let's call it c. If we compare with the code, we have rewritten this exact line as an equation. Well, almost. This 0x5 number is not exactly c, because there are some smarts built into it to compensate for the log 1 plus m equals m approximation. This approximation is in fact perfectly equal when m equals 0. Then we have the log of 1 which is 0, and for m equals 1, we have the log of 2 which is 1. In between, the log function is always slightly higher than the m line. Since by construction m is always between 0 and 1, we always underestimate it a little bit. In order to get a better approximation, one idea would be to shift this line upwards. The number 0x5 combines the shift into the c constant. I believe it was found by successive trials. So, if we put everything together, the function begins by defining numbers for the Newton-Raphson method. Then it uses the fact the log x is related to the int representation of x and log properties to obtain a good first approximation, and then refines this approximation using the Newton-Raphson method. And that's it. This is the end. Thanks for watching. See you next time. Or stay for a message from the sponsor of this video. Me. I'm the sponsor of this video. When facing a complicated thing, it's often helpful to break it into smaller chunks. I think this video demonstrates the effectiveness of this approach. Bye now.